So next topic is deformation of solids. Deformation of solid. It is possible to change the shape and size of an object through the application of external forces. It is described as strain. As deformations occur, internal intermolecular forces arises that oppose the applied force. If the applied force is not too great, these internal forces are sufficient to completely resist the applied forces and allow the object to resume a new equilibrium state and to return to its original state when the load is removed. The large applied force may lead to a permanent deformation of the object or even its structure field. Depending upon the type of material, size, and geometry of the object, the force applied various deformation may result. Next is elastic deformation. It is reversible. When the forces are removed, the object turns to its original shape. Elastomer and shape memory metals such as nitanol exhibit large elastic deformation ranges as does rubber. Elasticity is non-linear. Metals and ceramics show linear elasticity, means same rate of shear and stress. Linear elastic deformation is governed by Hooke's law. Sigma is equal to E small e, where sigma is a applied stress, E is a material constant or called Young's modulus or elastic modulus, and E is a resulting strain. The relationship indicates that the slope of stress and strain curve can be used to find the elastic or Young's modulus E, the elastic range, and when the molecule reaches its yield strength. At this point, plastic deformation begins. So this is graph between stress and strain. This is elastic region. This point is elastic limit. So this region is called plastic deformation region, and this point is brittle fracture. Elastic modulus. Elastic modulus is the constant of proportionality between stress and strain. The elastic modulus can be thought of as the stiffness of the material. A material with a large elastic modulus is a very stiff and difficult to deform. Elastic modulus, stress is equal to elastic modulus into strain. Young's modulus. Tensile strength is the ratio of external force to the cross-section area. So SI unit of stress are Pascal. One Pascal is equal to 1 Newton per meter square. The tensile strain is the ratio of change in the length to the original length. Strain is dimensionless and it is also called Young's modulus. F upon A is equal to Y, change in length upon original length. Plastic deformation. It is irreversible. Object in plastic deformation range with the first have undergo elastic deformation which is reversible, so the object will partly return to its original shape. Soft thermoplastic materials have a rather large plastic deformation range as to ductile metals such as copper, silver, and gold. For example of material with a large plastic deformation range is a wet chewing gum which can be stretched dozen of its time its original length. Hard thermosetting plastics, rubber, and ceramics have minimum plastic deformation range. Under the tensile stress, plastic deformation is characterized as strain hardening region, nicking region, fracture. Strain hardening region. First, material becomes stronger through the movement of atomic dissolution. Nicking region, reduction in cross-sectional area of specimen. It begins after the ultimate strength is reached. Material can no longer withstand the maximum stress and strain in the specimen rapidly increase. Fracture indicates the end of the plastic deformation. Nickel equation. The variation in the volume when applied pressure are defined by the way of numerous equations, among which the Haeckel theory is most vital. Haeckel measured that decline in the voids follows the first order kinetics connection with applied pressure. For compression method, Haeckel suggests the following equation. Natural log V upon V minus V alpha is equal to Kp plus V original divided by V original minus V alpha, which is equal to y is equal to mx plus c, where V is a volume of applied pressure P, V0 original is equal to original volume of the powder including the voids. V alpha is equal to volume of the powder excluding the voids. K is a constant related to the yield pressure of the powder. P is equal to applied pressure, has we know porosity. E is the ratio of the total volume of the void placed to the uh, sorry space to the bulk volume of the powder material. E is equal to V minus V alpha upon V. Replacing the value in the previous equation, it becomes natural log 1 upon E is equal to Kp plus V0 upon V0 minus V alpha.